Hello everyone, and welcome to this next lecture on my circuit simulator Python Power Electronics. And the topic of this lecture is going to be how to change the operating point of a PV panel. So as before, I'm going to start with the Google page, and I'm going to start by typing Python Power Electronics. And this takes me to the simulator web page, which is this one. I now start with tutorials because this is a tutorial, and you'll see this is currently the first tutorial which is there at this point of time. The title is Controlling the Operating Point of a PV Panel. If you're watching this later at a much future date, there may be further months, just keep in mind this is the name of the tutorial. I'll click here for the detailed report. So as before, it contains several links. There is a slideshow which I'm going to open soon. So this is the slideshow. I'll come to it soon. The simulation files, as before, are always hosted on my external Gumroad site. That is this one. You can pick it up if you want, if you find the simulation interesting. And there are some help links here. That is, how do you install the software, any other help related with the software. So with this, I'm going to start with the tutorial. So it is this one. So before I start off with the tutorial, I'll just go back to the tutorial page, and I need to say that this tutorial is a combination of previous two tutorials. Now, one of them is the simulation of the photovoltaic panel, that is a simulation panel, and I've given these two links here. That is, the tutorial is a combination of the previous two tutorials here and here. So one of them is the simulation model of photovoltaic panel, because this tutorial takes the entire simulation model of the photovoltaic panel, does not consider it as a DC source. And this second link is the tutorial which describes how the DC to DC converter that interfaces the PV panel is switched. So I would suggest, before starting off with this tutorial, have a look at these two links. So I'm assuming now that you have actually gone through those two links, or you already are familiar with those two things. And with this, I'm going to start this tutorial. So as I said before, in this tutorial, I'm going to describe how you can change the operating point of a PV panel. I'm not going to describe the entire maximum power point tracking concept. That will come in a future tutorial. It is merely how do you move the operating point of a PV panel on the PV characteristics by switching the edge bridge converter. So let's go to the next slide. So when I talk about the operating point, I mean the operating point of a PV panel on the PV characteristics, which is this one. As I've said before, a PV characteristic, a PV panel is different from, let's say, a battery or any other generator. In those, the current supplied by the generator is decided only by the resistance of the external circuit. In a PV panel, that is not the case. In a PV panel, the current and the voltage are functions of each other. So let's suppose, for example, at a given solar incident radiation and at a given cell temperature, the characteristic of a PV panel will be something similar to this. Now, as the solar incident radiation changes, this characteristic will change. As the temperature changes, this characteristic will change. But let us assume that these two are constant. That is, solar incident radiation is constant at some value, temperature is constant at some value. So therefore, the operating point of the PV panel will always lie on this curve. It could be anywhere on the curve, but it has to be on the curve. And I would suggest that you go back to the previous tutorial and have a look at these different operating points. So a brief description of this before. In a solar PV panel, you have two extreme conditions, that is point A, which is the open circuit, and point E, which is the short circuit. Now, in a PV panel, you can actually short circuit the panel without damaging it. You cannot short circuit a battery, but you can short circuit a PV panel. So if you short circuit a PV panel, the voltage is 0, but the current is equal to the short circuit current ISC. Similarly, if the panel is open at this point A, the voltage of the PV panel is VOC and the current is 0. And elsewhere, it's somewhere on this point. So let's start from point A, that is, the PV panel is open circuited. As we connect a load and we draw current from the PV panel, the point moves along this curve. That is, as the current keeps increasing, the point moves along this curve until finally the panel is short circuited and reaches this point. So there are three distinct zones in the PV panel. So, okay, the first one, these two are ellipses, and the third one is almost circle. Now these two ellipses are not desirable operating points of the PV panel. The reason, because you do not get the maximum power from the PV panel. It is this circle here which is the desired operating region of the PV panel, and in particular it is this point C where you would like your PV panel to be operating at. The reason, point C is your maximum power point. This is where you get the maximum benefit from your PV panel. So the question is, how do we move the operating point along this curve? Is it possible to control it? Because that's what's most important. If we can control the movement of this operating point, and therefore we can ensure that this operating point is always at point C, then the PV panel produces the maximum power. So this is what we will describe soon. So this is the layout, the complete circuit layout of the PV panel connected to the grid. Now I might have described some of it before, I'll just describe it again. On the extreme left is our PV panel. And as I said before, PV panel comes in different voltage ranges. What we assume is the PV panel produces a voltage of around 20 to 40 volts, typically around 30 to 35 volts. This is connected to an edge bridge converter. This edge bridge converter converts the DC voltage produced by the PV panel to a switched waveform, switched AC waveform. And because it is a switched AC waveform, we can feed it to a transformer. This transformer steps up the low voltage of the PV panel to a high voltage. And this high switched AC voltage is then rectified by a diode rectifier to form a high voltage DC bus. And this DC bus is then connected through a DC to AC converter to the grid. This is the entire layout. Now in this tutorial I will not describe this last part, that is, I will not describe the DC to AC converter and the grid. I will stop here. The idea is to describe how this edge bridge converter is controlled so as to change the operating point of the PV panel and what is the impact on this DC bus. So I'm going to start by describing each block in greater detail. Now the PV panel is connected to the edge bridge. This is the edge bridge converter. Again, I would strongly suggest that you refer to the previous tutorial where I described the switching of this edge bridge converter, the philosophy of the switching, and why we need to switch it in that manner. Here I'm going to assume that you know what happens. Now, just in case I need to describe, there are a couple of changes which we need to make. Number one, there is a diode which I show here. This diode is to block any current from going back to the PV panel. Remember, the PV panel is a generator. It has no business taking in current. If you supply current to a generator, you could seriously damage it. The reason is simple, because this current, if you supply it to a PV panel, it will cause excessive losses in the PV panel, increasing its temperature and may damage it. So never supply current to a generator unless there is an energy storage. If it's a battery, if it's a supercapacitor, you can supply current, but you do not want to supply current to a generator. This diode therefore blocks any current from going into the PV panel. It will only allow current coming out of the PV panel. After this diode, there is a DC capacitor. The purpose of this DC capacitor is to ensure that the DC bus of this edge bridge converter is a smooth voltage. Remember, if you directly connect this edge bridge converter to the PV panel, the switching of the edge bridge converter could disrupt the operation of the PV panel. Remember, the PV panel has a variable voltage and current. Therefore, you do not want the switching of this DC capacitor, of this edge bridge converter, from disrupting or producing a fluctuating voltage of the PV panel, because that again could end up disrupting the operation of this edge bridge converter. So this DC capacitor acts as a decoupling capacitor that provides a constant smooth DC voltage so that this edge bridge converter can operate without any disruptions, and therefore this PV panel also does not directly feel the impact of the edge bridge converter switching. So with this, I'll now go to the next slide, and in this slide I'm going to continue. So now that we have this edge bridge, as I said before, the reason why we have this edge bridge converter is so that we can convert the DC voltage to a pseudo AC voltage waveform. For this, please again visit the previous tutorial. And therefore, when we have a pseudo AC voltage, we can use a transformer. Now this transformer is not a regular line frequency transformer, it's a high frequency transformer because we have a switched high frequency AC voltage. But this high frequency transformer now produces a high voltage AC on its secondary. So we have been able to convert a DC voltage, essentially we've been able to convert the DC voltage of the PV panel to a high frequency switched AC voltage. And that's what this part of the circuit does. So now that this is over, go to the next slide. And as I said, this transformer secondary now has a high voltage, high frequency switched AC voltage waveform. Now we want to convert this back to DC. The reason is because we cannot directly use this to supply our loads. We have to now connect it to a grid. The grid is a 50 Hz, 60 Hz AC grid. So therefore, the only way to actually convert this high frequency AC voltage to a grid frequency AC voltage is by converting it first to DC. And for that reason, we have this diode rectifier. Now this diode rectifier has a filter inductor. The reason is simple. If you have a high frequency switched AC waveform here and you directly try to feed it to a DC capacitor through a diode rectifier, the current spikes are going to be so high if there is no filter that this may actually end up damaging the diode and the DC capacitor. So we need a filter to smoothen out the current spikes. So as you can see, in this entire topology, there is only one, of course, I am not talking about the DC, as I said before. In this entire topology, terminating at this DC capacitor, there is only one controllable component, and that is this edge bridge converter. So therefore, all our control is going to be the switching of this edge bridge converter. The diode is just a passive rectifier. It just converts AC to DC. It cannot control any other aspect of it. So if you want to control the magnitude of voltage, if you want to control the power flow, which I'll talk about soon, it is the switching of the edge bridge which has to be controlled. So the focal point of this control description will therefore be the edge bridge converter. So at this point of time, again, if you need details, please go back to the previous tutorial, but I'm going to assume that you know what these switching waveforms are. So this is the edge bridge waveform, edge bridge converter. There are 4 switches with their anti-parallel diodes. Now, as I said before, in any leg, switch S1, S2 cannot be connected together, cannot be switched on at the same time, because if you switch these two devices on at the same time, you'd short circuit the DC bus. The current will be so high that the switches and the DC capacitor will be damaged. So switch S1 and S2 will always be complementary. They cannot be on at the same time. If S1 is on, S2 has to be off. If S2 is on, S1 has to be off. And the same for switches S3, S4. Now, between these legs, that is this first leg and the second leg, we now have some freedom. And I'm going to talk about that through this waveform. If you look, switch S1 and S2 are complementary. That is, S1 is off, S2 is on. S1 is on, S2 is off. And the same for S3 and S4. But S3 and S4 are phase shifted with respect to S1 and S2. And the result is we have this switched voltage at the output of the edge bridge. So this is the switching combination that results. We have S1 on, S3 on, S2 off, S4 off. That is this particular region. Then the next region, we have S1 on, S4 on, S2 off, S3 off. And therefore, and these two. So look at these 4 regions marked here. That is what has been marked in this point. Alright, I won't just read them out because in the next few slides, I'll talk about the significance of these switches. So now, what happens when S1, S4 are on and S3, S2, S3 are off? So I have only shown S1, S4 for emphasis. When S1, S4 are on, you'll see that the current path is in this direction. The DC capacitor is connected directly through the DC capacitor through this path. You see? So therefore, in this particular condition, power is transferred from the DC capacitor to the output DC capacitor. Alright? This is a driving state of the H-bridge converter. And I'll show you why it differs. Now let's look at the other condition. S2 and S3 are on, S1 and S4 are off. Even in this condition, you'll find that actually this is still a driving condition. Let's look at this. This is the rate at which the current flows, and you see this is the path. Also, in this case, power again is transferred from the PV to the DC output DC capacitor. The only difference is here I am producing a negative voltage, but still power is transferred from the PV to the DC capacitor. What happens in the other two states? When S1 and S3 are on, but S2 and S4 are off, something very different happens. Now, I've shown both these devices because you never know how it works. Let's say the current is flowing in this direction. That is, S1 is conducting. So if S1 is conducting, this is the path in which the current flows. Now, out of these devices, which will conduct? S3 cannot conduct because the current will flow in the reverse direction through S3. Remember, a switch can only conduct current in one direction. It cannot conduct current in the reverse direction. In this case, it is the diode which conducts. So you see the current through this inductor, which is basically the filter inductor, freewheels through switch S1 and the diode across the switch S3. The PV panel is not connected to the output DC capacitor. Remember, this H bridge is completely disconnected from the left part of the circuit. It is the DC output capacitor does not produce any current. And now let's look at what happens when S2 and S4 are on. Again, the same condition. Let's suppose, for example, the current is flowing in this direction. If the current is flowing in this direction, this is the path in which the current flows. So if the current flows in this path, S4 will conduct because diode cannot conduct. The current is flowing in this direction. But here, if the current is in this direction, it is switch S2 cannot conduct. Why? Because the switch S2 cannot conduct current in the reverse direction. It is the diode across the switch S2 will conduct. So again, in this condition, current can flow in either direction. This is to be noted here. In this condition and also in this condition, the current can flow in either direction. Only thing that matters is if the current is trying to flow in a direction which is reverse to the switch, the switch will not conduct. It is the diode which will conduct. So therefore, in both these cases, the PV panel is not connected to the DC capacitor. The PV panel does not supply any current to the DC capacitor. Now, I would suggest at this point of time that you pause the video, try to go back to these slides and try to map these 4 switching conditions to these 4 switch states. I would suggest that you do so before continuing with this video. Pause the video right now, figure this out, take a pen and paper if you need to, and just draw these figures and continue only when you are sure that you know what's going on. So I'm now going to look at how we're going to continue from here. So as I said before, there is an impact to that switching. This is the current at the DC link of the H-bridge converter. Now I'm going to show you exactly where this happens. It is this part which I'm looking at. Alright, not the current in the DC capacitor, but is the current in that DC link. And I'll tell you why this is important very soon. But as I said, when switches S1, S4 are on, or S2 and S3 are on, it is a driving state of the H-bridge converter. That is, current is transferred from the PV panel to the output DC capacitor, and that's when you see a current in that H-bridge link. When S1, S3 are on, or S2 and S4 are on, the current is 0, because remember, the inductor current freewheels through the switches. It does not pass through the DC link, and that's why you see the current through the DC link is 0. And this is extremely important. Why? Because this pulse, this current pulse, can now be changed by changing the pulse width of the H bridge. And I'll show you what happens. This is one particular random H bridge pulse width. But let's suppose for this I would suggest going back again to the previous slide, previous tutorial, and you will find that the pulse width of that AC waveform can be changed by changing the phase shift between the two legs. So what happens if I decrease the pulse width? You see, this is what happens when you decrease the pulse width. The current pulse in the H bridge decreases. Why is this significant? Take this current and take this current. Both of them have a DC component. They are not DC currents because quite obviously they are not constant currents, but they have a certain DC component. Now this DC component is totally dependent on the pulse width. Greater is the pulse width, greater will be the DC component. For example, the DC component of this current is going to be much larger than the DC component of this current. Quite obviously, because why? Because the pulse width is much smaller in this case than in this case. So therefore, this is a very important point. By increasing the pulse width, I am increasing the DC component of the current in the H bridge link, the DC link of the H bridge. Why is that important? I'll talk about it in the next slide. Now let's look at this particular DC link only. Alright, because I showed you the current waveforms of this current. This is the current in the DC link, and these were the waveforms I showed you before. Let us now, as is in any circuit, Kirchhoff's current law is always applicable, which means at this point Kirchhoff's current law is applicable. The PV current is equal to the sum of the DC link current and the sum of the current going into the DC capacitor. So if I have a larger DC link component, so that is if this DC component of the current in this link IDC is larger, the current through the DC capacitor is going to be smaller, because remember, for a certain PV current, the larger one component is, the smaller the other component is. So by changing this DC link, I am now able to change the current through the DC capacitor. What does that mean? If I change the current through the DC capacitor, I can now change its voltage, right? What does this mean? I am now changing by controlling the switching of this H bridge converter, I am able to control the DC component in the DC link. And by controlling this current in the DC link, I am able to control the voltage of the DC capacitor. Why is this significant? Next slide. Now let me just look at this, the PV panel and the DC capacitor separated by this diode. Now, as I said before, the diode's purpose is to protect the PV panel and not let a current go into the PV panel. But usually this diode will always be on. It is only off in abnormal conditions, and I'll talk about that in a later tutorial. I'll tell you why when that happens. But let us say in this case that the diode is on. If the diode is on, the difference between the PV panel voltage and the DC capacitor voltage will be this diode drop, which means the resistance of this diode multiplied by the PV current. The resistance of a diode when it is on is negligible, which means the drop is negligible. And what that means is that the DC capacitor voltage is approximately equal to the PV panel voltage. So now, why is that significant? Why is that significant is, now we have found a way to control this DC capacitor voltage, and by controlling this DC capacitor voltage, we are indirectly controlling the PV panel voltage. And now, why is that significant? Let's go back to this PV characteristic. As I said before, the operating point has to be on this curve. So if I change the voltage of the PV panel, it will always move. For example, let's say I have this voltage at point A, open circuit voltage. If I decrease the PV panel voltage by some means, the operating point will move along this point, along this path. It has to stay on this PV curve. If I control one variable, if I control the PV panel voltage, I am controlling the operating point. All right. You could also see if you control the PV panel current, you would also end up controlling this operating point. But in this case, I have found a way to control this PV panel voltage. How? By switching the H bridge converter, by changing the DC link current voltage, therefore changing the DC capacitor current, and then changing the DC capacitor voltage. So this is the way we control this PV panel voltage. So how is this happening? I'm going to show you this in a simulation result. Now this is a simulation that I have performed. Okay. Now this is a simulation that takes over like 0.3 or 0.4 seconds, and it starts from the beginning. Initially everything is zero, which means the DC capacitor voltage is zero, the output capacitor is uncharged, everything is uncharged. And what that means is, and I'll show you how this means. Okay, let's go to the next slide. Let's say at startup. When it is at startup, the blue line is the PV current. The orange line is the PV voltage. The green line is the output voltage at the terminating DC capacitor. When at this point, starting point, as I said, everything is uncharged. So the DC output capacitor, and when I say, I should just clarify here, this DC capacitor is totally uncharged. It has zero voltage. And when it has zero voltage, that indirectly means the PV panel is short circuited. When the PV panel is short circuited, the current of the PV panel is at its short circuit value, and that's what this value is. It's around 9.6 amperes. That's dependent, that you can pick that up from the data sheet. Because it is at short circuit current, another aspect is until 1 millisecond I am not switching my H bridge converter. That is why you see the DC output capacitor has zero charge, because nothing is flowing to the DC output. The H bridge is not charged, H bridge is off. Because of that, slowly the DC capacitors are charging. Why? Because this PV panel current is flowing into it. Obviously it will start charging. At 1 millisecond, I am now starting switching the H bridge. And as I start switching the H bridge, the voltage of the output DC capacitor, that is at the extreme end, starts rising. Now, how does this entire simulation work? For that, I'll just show you the next slide. I am starting and for this, I would suggest go back to the previous tutorial and talk about and see how the phase shift is generated. Now, the phase shift produces a varying AC voltage. So I am now starting with a phase shift of 140 degrees, all right, at initial starting point. So that is starting from here. The minute the H bridge is switched on, the phase shift is 140 degrees. And every 0.02 seconds, I am decreasing this phase shift by 10 degrees. And I continue this process until finally I am at 0 degrees. All right. So let's see what happens at this operating point. Now, let's go back here. You see here, the voltage up till here, the current is at almost short circuit value. And that's what we look at here. As we increase the PV panel voltage, the PV panel voltage is continuously increasing. You see, the PV current is gradually decreasing. And here, when we reach 0 degrees, the PV current is 0 and the voltage is at open circuit value, open circuit voltage. So we are moving from almost a short circuit condition to an open circuit condition. So essentially what we are doing is we are moving from this point E all the way up to point A. All right. As this voltage increases, you see the voltage of the PV panel keeps increasing. This current this operating point gradually moves along this operating point. You see the current, the voltage gradually increases, reaches the maximum power point and keeps going until it reaches the open circuit voltage. What happens? What actually happens here? As I decrease the phase shift, I am decreasing the DC component of the current in the DC link. What that means is that the voltage of the PV panel is now allowed to increase. And as the voltage of the PV panel is allowed to increase, the operating point now moves along the PV panel curve. So this is how we change the operating point of the PV panel, by changing the phase shift of this H-bridge converter. And as you can see, this output DC capacitor is charging at the highest rate at around this point. What that means is somewhere around here is your maximum power point. And as time goes on, as you keep increasing the phase shift, the voltage keeps increasing, you finally end up losing, the power starts decreasing, until finally you see here the power is completely, and at this point the power is 0, and that's when this DC output DC capacitor is completely going to discharge to 0. So this shows how the power flows from the PV panel to the output DC capacitor. Through this by changing this phase shift of the DC converter, of the H-bridge converter, sorry. So that's what this entire this tutorial was. I would suggest go through these links once again if you need clarification. But this tutorial has shown how phase shift control changes the operating point of the PV panel by indirectly changing the DC link current, which in turn changes the DC capacitor current, which in turn changes the DC capacitor voltage, and that indirectly sets the PV panel voltage. So what this has shown is, that phase shift control allows you to move all along the PV characteristic. We moved from short circuit to open circuit, and this is what lays the foundation for maximum power point tracking. This is a concept which will not be explained here, which will be explained in a future tutorial, but this is the concept. So with this, I'll end this tutorial. As before, if you're interested in knowing more, check out the package. The simulation files are provided in the package, and if you need more information, check out the website. That's all for now. I'll probably release the next tutorial in a few weeks. Stay tuned. Thank you so much. Goodbye for now.